Picture this. The entire universe is like a giant microwave oven that's been running for 13.8 billion years. And what's left behind isn't just heat, but an ancient, crackling afterglow from the very birth of everything. That's the cosmic microwave background, or CMB for short. It's not just distant light or some cosmic static. It's literally the oldest baby picture of our universe, frozen in time and stretched into microwaves across the void of space. But here's the wild part. This faint glow is everywhere, even in the empty spots between galaxies, and it holds secrets that could rewrite our understanding of reality. Like how it accidentally proved the Big Bang while two astronomers were cleaning pigeon droppings off their antenna, or how tiny temperature variations in it, smaller than a speck on a pizza, decided where galaxies would form. And that's just the start. Over the next few minutes, we're diving into 25 mind-blowing facts about the CMB that will make you see the universe, and maybe even yourself, differently. Because guess what? The atoms in your body were forged in the same fiery plasma that created this cosmic echo. So stick around, this isn't just space trivia. It's your origin story. Here's the next section of your script, seamlessly continuing from the previous part while introducing the first mind-blowing fact about the cosmic microwave background. Now, let's zoom in on the first jaw-dropping detail about the CMB. It's everywhere. Imagine turning on an old television set and seeing that familiar snow-like static, the kind that used to fill screens when channels went off the air. That flickering noise wasn't just random interference. Believe it or not, about 1% of that snowy static was actually the faint whisper of the cosmic microwave background, bleeding through time and space to reach your living room. This glow isn't just lingering in some far-off corner of the cosmos. It's literally everywhere, saturating every cubic inch of the universe, from the vast voids between galaxies to the seemingly empty space right in front of your face. Wherever you are right now, you're submerged in an ocean of ancient radiation left over from the Big Bang. It's like being inside a giant, invisible fingerprint of creation itself. But here's what makes it even wilder. The CMB isn't just present, it's nearly uniform. Picture a room where every single point, from the floor to the ceiling, is the exact same temperature, down to a fraction of a degree. That's the CMB, a staggering 2.7 Kelvin, or about -454 degrees Fahrenheit. No matter where you look, the tiny fluctuations in that temperature, those minuscule hot and cold spots, are the real goldmine, though. They're the faint echoes of quantum jitters from the universe's infancy, the seeds that eventually grew into galaxies, stars, and even us. So the next time you stare at the night sky, remember you're not just looking at distant stars. You're swimming in the afterglow of the universe's birth, a signal so pervasive that it quietly hums in the background of existence itself. And this is just the first clue in our cosmic detective story. Now let's peel back another layer of this cosmic mystery. The cosmic microwave background isn't just everywhere, it's also the oldest light in the universe, a snapshot frozen in time. Picture this: for the first 380,000 years after the Big Bang, the universe was a seething, opaque fog of charged particles, so dense that light couldn't travel more than a tiny distance before being scattered. It was like trying to see through a wall of molten lava. But then, something extraordinary happened. As the universe expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms, clearing the cosmic fog in what scientists call recombination. Suddenly, light could travel freely for the first time, and that burst of photons, still glowing from the heat of creation, is what we now detect as the CMB. Think of it as the universe's first baby photo, a glimpse of what it looked like before stars, galaxies, or even dust existed. What's mind-blowing is that this light has been traveling for over 13.8 billion years, stretched and dimmed by the expansion of space itself. Those microwaves hitting our telescopes today began their journey when the cosmos was a mere infant, 1,000 times smaller and hotter than it is now. And here's the kicker: because light takes time to reach us when we observe the CMB, we're literally looking back in time to the universe's toddler phase. It's the ultimate time machine, letting us study the dawn of everything. But this ancient light isn't just a relic, it's a Rosetta Stone for cosmologists. Those tiny temperature fluctuations we mentioned earlier, they're like fingerprints of the universe's earliest structures, hints of the gravitational tug of war that would eventually sculpt galaxies. By decoding these patterns, scientists can test theories about the Big Bang, dark matter, and even the universe's shape. So the next time you hear about the CMB, remember, you're not just hearing about faint microwaves. You're witnessing the afterglow of the universe's very first sunrise. Now, let's talk about one of the most surprising things about the cosmic microwave background: its temperature. You might expect something as ancient and vast as the CMB to have wild variations, but here's the twist: it's almost perfectly uniform. Across the entire sky, no matter where you look, the temperature of this cosmic glow hovers around 2.7 Kelvin. That's just a hair above absolute zero, the coldest temperature possible in the universe. To put that in perspective, 2.7 Kelvin is about -454 degrees Fahrenheit, so cold it makes the depths of space seem warm by comparison. But here's where it gets even more fascinating. While the temperature is nearly the same everywhere, it's not exactly the same. Imagine a pizza fresh out of the oven, mostly evenly baked, but with tiny spots that are slightly hotter or cooler than the rest. The CMB is like that, a cosmic pizza with minuscule temperature variations, about 1 part in 100,000. These tiny differences might seem insignificant, but they're actually the fingerprints of the universe's infancy, holding clues to how everything we see today came to be. These fluctuations, called anisotropies, are the result of quantum jitters in the early universe, tiny ripples in density that were magnified by the rapid expansion of space during cosmic inflation. Think of it like blowing up a balloon with faint ink marks on it. As the balloon inflates, those tiny marks stretch into larger patterns. In the same way, those microscopic irregularities grew into the seeds of galaxies, galaxy clusters, and the vast cosmic web we observe today. Without these subtle hot and cold spots, the universe might have remained a featureless void, with no stars, planets, or us to ponder it. Scientists have mapped these temperature variations in incredible detail using satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory. These maps are like treasure troves for cosmologists, revealing not just the structure of the early universe but also deeper mysteries like the amount of dark matter and dark energy, or even the geometry of space itself. So next time you hear about the CMB's temperature, remember, it's not just a number. Those faint fluctuations are the universe's way of whispering its secrets to us, written in the language of heat and light. And the more we listen, the more we uncover about the grand story of everything. Now, let's take a step back in time to uncover one of the most serendipitous discoveries in science: how the cosmic microwave background was first detected. Picture this: it's 1964 and two radio astronomers, Arno Penzias and Robert Wilson, are working at Bell Labs in New Jersey, fiddling with a giant horn-shaped antenna originally built for satellite communications. But there's a problem. No matter where they point this antenna, they pick up a persistent, annoying hiss, a uniform microwave signal coming from every direction in the sky. At first, they assume it's just interference. Maybe it's radio noise from nearby New York City, or perhaps faulty equipment. They even considered an unlikely culprit: pigeon droppings. That's right, a pair of pigeons had nested inside the antenna, leaving behind what Penzias later called a white dielectric material. The duo cleaned it all out, even resorting to what Wilson described as a low-tech solution, shooing the pigeons away with a shotgun. But the hiss remained. Here's where things get interesting. Meanwhile, just 30 miles away at Princeton University, a team led by physicist Robert Dicke was actively searching for this very signal. They'd predicted that if the Big Bang really happened, the universe should be filled with a faint afterglow, cooled microwaves from its fiery infancy. When Penzias and Wilson heard about Dicke's work, the pieces clicked. That stubborn hiss wasn't interference, it wasn't pigeon leftovers, it was the echo of creation itself, the cosmic microwave background. The discovery was groundbreaking. Before this, the Big Bang theory had rivals like the steady-state model, which argued the universe had no beginning and no end. But the CMB was the smoking gun. It proved the universe wasn't eternal, it had a hot, dense origin. For their accidental detective work, Penzias and Wilson won the Nobel Prize in Physics in 1978, cementing the CMB as one of the strongest pieces of evidence for the Big Bang. What's wild is how humble the discovery was. No fancy space telescopes, no billion-dollar missions, just two curious scientists, a problematic antenna, and some very persistent pigeons. It's a reminder that sometimes the biggest cosmic revelations come from the most unexpected places. And thanks to their troubleshooting, we now have a window into the universe's first moments written in microwaves. Here's how you might smoothly transition and expand on this section while maintaining engagement and clarity. But here's the real game changer. The discovery of the cosmic microwave background didn't just solve a mystery, it ended a cosmic debate. Up until the 1960s, scientists were split between two competing theories about the universe's origin. On one side, you had the Big Bang model, which suggested the cosmos began in a hot, dense state and has been expanding ever since. On the other side was the steady-state theory championed by astronomers like Fred Hoyle, who famously coined the term Big Bang, ironically as a dismissive nickname. The steady-state model argued that the universe had no beginning or end. Instead, new matter was continuously created to fill the gaps as space expanded, keeping the cosmos looking roughly the same at any point in time. So why did the CMB tilt the scales? Because the steady-state theory couldn't explain it. If the universe truly had no beginning, there'd be no reason for it to be bathed in a uniform glow of microwaves, a fossil remnant of an ancient hot phase. The CMB's near-perfect uniformity and its precise temperature of 2.7 Kelvin matched exactly what the Big Bang model predicted, the cooled remains of a primordial fireball. For the steady-state camp, this was a fatal blow. There was no way to tweak their theory to account for the CMB without contradicting its core principles. Even more damning, the CMB's tiny temperature variations, those 1 part in 100,000 wrinkles we mentioned earlier, aligned perfectly with the idea of a dynamic, evolving universe. They were the seeds of galaxy clusters, evidence that structure grew over time, not something static or eternal. By the late 1960s, most scientists had switched sides. The Big Bang wasn't just a compelling idea anymore. It was the only framework that could explain the evidence. What's fascinating is how quickly the paradigm shifted. Just a few years before Penzias and Wilson's discovery, the steady-state theory was a serious contender. But science has a way of settling debates with data, and the CMB was the ultimate referee. It didn't just support the Big Bang, it made the theory unavoidable. And that's the power of a single, stubborn hiss in a New Jersey antenna. It rewrote the story of our cosmic origins. This keeps the narrative flowing, adds historical context, and reinforces the CMB's pivotal role, all while avoiding repetition and maintaining an engaging conversational tone. Now, let's zoom in on something truly mind-bending, those minuscule imperfections in the cosmic microwave background. At first glance, the CMB appears incredibly smooth, like a perfectly blended cosmic latte. But look closer and you'll spot the wrinkles. These tiny temperature variations, just 1 part in 100,000, might seem insignificant, but they're the universe's original blueprints. Imagine blowing up a balloon with faint, barely visible creases. Over time, as the balloon expands, those tiny wrinkles stretch and grow, transforming into pronounced ridges and valleys. That's exactly what happened with the CMB. Those subtle fluctuations were the seeds of everything we see today: galaxies, clusters, and the vast cosmic web. Without them, the universe would have remained a featureless soup of particles, and we wouldn't be here to ponder it. What caused these wrinkles? Think of the early universe as a boiling pot of plasma, where quantum jitters, tiny, random fluctuations at the smallest scales, left their mark. As the universe expanded, those microscopic ripples were magnified, frozen into the CMB when light finally broke free. Then, over billions of years, gravity got to work, pulling matter into denser regions, sculpting the cosmos into the structured tapestry we observe now. Here's where it gets even wilder. Scientists can actually read these fluctuations like a cosmic barcode. Warmer spots in the CMB indicate denser regions where extra matter clumped together, while cooler spots reveal emptier patches. By mapping these patterns, we've uncovered the universe's recipe, a precise mix of ordinary matter, and dark energy. It's like decoding the universe's DNA, one microwave photon at a time. And the precision is staggering. Those 1 part in 100,000 variations weren't just random noise. They followed a specific mathematical pattern predicted by theories of cosmic inflation, a rapid expansion spurt in the universe's first fraction of a second. This match between prediction and observation is one of the strongest validations of modern cosmology. So the next time you gaze at the night sky, remember, the grand structures you see, the swirl of galaxies, the glow of nebulae, all trace back to those faint wrinkles in the CMB. It's a humbling thought. The universe didn't start out smooth. It started out almost smooth, and those tiny imperfections made all the difference. Now, let's peel back another layer of the cosmic microwave background's mystery: its polarization. You might think of light as just waves rippling through space, but those waves can actually have a preferred direction, like ocean waves rolling toward shore. That's polarization, and the CMB has it too. This faint but detectable property isn't just a curiosity, it's a goldmine of information about the universe's infancy. When the CMB was born, light finally broke free from the hot, dense plasma that filled the early universe. But as those photons traveled, they bumped into the first atoms, forming mostly hydrogen, and that interaction left a subtle imprint, a slight polarization in the light. Think of it as the universe's first fingerprint, a ghostly signature of the moment matter and light went their separate ways. Scientists call this E-mode polarization, and it's like a snapshot of those primordial atoms taking shape. But here's where things get even more intriguing. There's another type of polarization hidden in the CMB called B-mode, and it's far harder to detect. These twisted, swirling patterns aren't from atoms. They're thought to be the fingerprints of gravitational waves, ripples in spacetime itself, generated during cosmic inflation. That's the mind-blowing idea that the universe expanded faster than light in its first tiny fraction of a second. If confirmed, B-modes would be direct evidence of inflation, giving us a glimpse into physics at energies far beyond anything we can recreate in labs. Detecting these faint signals is like trying to spot a single candle flicker next to a spotlight. Earth's atmosphere, galactic dust, and even the instruments themselves can muddy the data. That's why projects like the BICEP and Planck collaborations have spent years meticulously mapping the CMB's polarization, filtering out noise to isolate these cosmic whispers. In 2013, BICEP-2 made headlines with a potential B-mode detection, though later analysis suggested dust might have mimicked the signal. The hunt continues, with next-generation telescopes aiming to settle the debate. Why does this matter? Polarization doesn't just tell us what happened, it tells us how. E-modes reveal the universe's first atoms, while B-modes could unveil the violent birth of spacetime. Together, they're like the universe's diary with pages written in microwaves. And every new measurement brings us closer to answering the biggest questions. What sparked the Big Bang? Are there other universes? The CMB's polarized light might hold the clues. So the next time you hear about the cosmic microwave background, remember, it's not just a uniform glow, it's a cosmic storybook with each polarized photon whispering secrets about our origins. And we're just learning how to listen. Here's your next section, seamlessly continuing the script with a fresh and engaging approach. Now, let's unravel another mind-bending twist about the cosmic microwave background, its dramatic transformation from blinding light to faint microwaves. Picture this: when the CMB first burst into existence, it wasn't the subtle glow we detect today. It was a blazing sea of visible light, as bright as the surface of the sun. But over 13.8 billion years, the universe stretched like an endless rubber band, and that light stretched with it, shifting all the way into the microwave range. Here's how it works. As the universe expands, space itself stretches, and the light traveling through it gets redshifted. Its wavelengths grow longer, sliding down the spectrum. Imagine drawing a wave on a rubber band, then pulling both ends. The wave stretches out just like the CMB's light did, shifting from visible yellow to infrared and finally to microwaves. That's why we don't see the CMB with our eyes. It's been stretched 1,000 times longer than its original wavelength. This redshift isn't just a cosmic quirk, it's direct proof of the universe's expansion. When astronomers like Edwin Hubble first noticed galaxies moving away from us, their light was redshifted too, but the CMB takes it to another level. It's the oldest redshifted signal we have, a fossil of that initial expansion. And just like tree rings tell a tree's age, the amount of redshift in the CMB pins down the universe's age to 13.8 billion years. But here's the kicker: this process is still happening. The universe keeps expanding and the CMB's light keeps stretching. In another few billion years, it might shift into radio waves, fading further into the cosmic background. It's a reminder that the universe isn't static. It's a living, breathing entity, and the CMB is its heartbeat, slowing but never stopping. So when you hear about the cosmic microwave background, remember, it's not just ancient light. It's light that's been on an epic journey, stretched across time and space to whisper its story to us today. Now, let's take a closer look at how scientists have transformed the cosmic microwave background from invisible whispers into a visual masterpiece. If you've ever seen a map of the CMB, you might have noticed it resembles a speckled egg, a canvas of tiny, colorful dots scattered across deep space. But these aren't just random splatters. Each speckle is a fossilized imprint of the universe's infancy, a snapshot of density variations that would one day grow into galaxies, stars, and even us. The story of these maps begins with satellites like WMAP and Planck, cosmic cartographers that spent years scanning the sky. They didn't just capture the CMB's temperature, they measured its faintest fluctuations with precision finer than a millionth of a degree. Think of it like listening to a symphony and isolating every single instrument. The result, a map so detailed it reveals the universe's blueprint, those hot and cold spots you see. They're the echoes of quantum jitters from the Big Bang itself. In the early universe, matter wasn't spread evenly. Tiny overdensities, regions where particles clumped slightly tighter, created gravitational wells. These spots appear warmer in the CMB because photons had to fight harder to escape them, losing a bit of energy along the way. Meanwhile, underdense regions let photons zip through easily, leaving cooler patches. It's like stepping out of a sauna into a snowstorm. The temperature difference tells you where the energy went. The colors on the map aren't just artistic flair. Blue hues mark the coldest areas, red the warmest, and everything in between paints a gradient of the universe's baby wrinkles, the most striking feature. The overall uniformity. Those fluctuations are incredibly subtle, just 1 part in 100,000, yet they held the seeds for everything we see today. Stretch those speckles over billions of years, add gravity's pull, and voila! Galaxies, clusters, and cosmic webs emerge. But here's what makes these maps revolutionary. They're not just pretty pictures. By analyzing the pattern of spots, scientists can test theories about cosmic inflation, dark matter, and even the universe's shape. The CMB map is like a Rosetta Stone for cosmology. Decoding it has rewritten our understanding of space and time. So next time you see that speckled egg in the sky, remember, you're staring at the universe's first selfie, a Polaroid taken when everything was just getting started. Now let's peel back another layer of the cosmic microwave background's mystery, this time to uncover one of the universe's best-kept secrets, dark matter. You've probably heard of this elusive substance, the invisible scaffolding that holds galaxies together. But how do we even know it exists? Believe it or not, the CMB is like a cosmic detective, and its clues are written in those tiny temperature fluctuations we just talked about. Here's how it works. Dark matter doesn't emit, absorb, or reflect light, so it's literally invisible to telescopes. But it does have gravity, and that gravity bends the path of CMB photons as they travel across the universe, a phenomenon called gravitational lensing. Imagine the CMB as a flashlight beam shining through a frosted glass pane. The pane's imperfections distort the light, revealing its texture. Similarly, dark matter's gravitational pull warps the CMB's light, leaving subtle imprints that satellites like Planck can measure. By studying these distortions, scientists can map where dark matter lurks and even estimate how much of it is out there. The numbers are staggering. Dark matter makes up roughly 27% of the universe's total mass energy. To put that in perspective, all the stars, planets, and galaxies we see, the so-called normal matter, account for just 5%. The CMB's patterns confirm this imbalance. Those hot and cold spots we see, their sizes and distributions align perfectly with models where dark matter's gravity sculpted the early universe. Without it, galaxies would have never formed, and the cosmos would look eerily empty. But the CMB doesn't just tell us dark matter exists, it hints at what it's made of. Most theories point to WIMP, or weakly interacting massive particles, hypothetical subatomic particles that barely interact with normal matter. The CMB's fluctuations rule out alternative ideas like primordial black holes because their gravitational signatures don't match the data. It's like narrowing down a suspect list using fingerprints. Here's the kicker: the CMB also reveals how dark matter behaves. Its patterns show that dark matter must move sluggishly, or else those primordial density variations would have smoothed out too quickly for galaxies to form. This cold dark matter scenario is now the leading theory, all thanks to the CMB's meticulous testimony. So next time you hear about dark matter, remember, it's not just a placeholder for our ignorance. The cosmic microwave background has given us a receipt, a detailed ledger of its influence, its quantity, and even its personality. And as we decode more of its secrets, we're not just solving a cosmic whodunit. We're rewriting the story of how everything, including us, came to be. Just when you thought the cosmic microwave background couldn't get more fascinating, it hands us another cosmic bombshell: dark energy. If dark matter is the universe's invisible scaffolding, dark energy is its mysterious engine, pushing everything apart at an ever-increasing speed. And guess what? The CMB holds the blueprints to this enigmatic force too. Here's the mind-bending part. When scientists mapped the CMB's large-scale patterns, they noticed something odd. The universe isn't just expanding, it's accelerating. Those tiny temperature fluctuations we've been talking about, their distribution across the sky matches perfectly with a universe where dark energy dominates, making up a staggering 68% of the cosmos. To put that in perspective, dark energy outweighs dark matter by more than double and dwarfs ordinary matter by over 13 times. It's the universe's biggest ingredient, and we can't even see it. How does the CMB reveal dark energy? It's all about geometry. the CMB's patterns act like a cosmic ruler measuring the universe's shape and expansion history. Think of it like this: if you toss a pebble into a pond, the ripples spread out in a predictable way. But if the pond starts stretching faster and faster, those ripples would look distorted. The CMB shows us similar distortions, subtle shifts in the size and spacing of those hot and cold spots. That only makes sense if dark energy is stretching spacetime itself. The real kicker: dark energy's effect only became noticeable about 5 billion years ago. Before that, gravity was winning the cosmic tug of war, slowing the expansion. But then, dark energy took over, and now galaxies are racing away from each other faster than ever. The CMB captures this turning point in the universe's life story, like a snapshot of its rebellious teenage phase. What exactly is dark energy? That's the million-dollar question. The leading theory is the cosmological constant, a kind of energy baked into empty space itself. Einstein actually dreamed it up back in 1917, then called it his biggest blunder. Turns out he might have been right all along, but the CMB also leaves room for wilder ideas like quintessence, a dynamic energy field that changes over time. Either way, the CMB's data is our best guide to solving the puzzle, and here's why this matters. Without dark energy, the universe's fate would be bleak, a slow, cold collapse. Instead, we're headed for an infinite stretch where galaxies vanish over the horizon and the cosmos grows dark and lonely. The CMB doesn't just tell us where we came from, it hints at where we're going. So next time you hear about dark energy, remember, it's not just some abstract idea. The cosmic microwave background has handed us the receipts, proving that the universe is running on a fuel we're only beginning to understand. Now, let's take a sharp turn from dark energy to another jaw-dropping revelation hidden in the cosmic microwave background: the shape of the universe itself. If you've ever wondered whether the cosmos is curved like a ball or warped like a saddle, the CMB has the answer, and spoiler alert, it's probably as flat as a pancake. Here's why that's mind-blowing. For centuries, physicists debated whether parallel lines would eventually cross or drift apart, depending on the universe's geometry. But the CMB settled the argument with cold, hard data. Those tiny temperature fluctuations we keep mentioning, their patterns act like a cosmic tape measure, revealing that space-time is flat to within a razor-thin margin of error, less than 2%. Picture this: if you fired two laser beams straight ahead in a perfectly flat universe, they'd stay parallel forever, never converging or diverging. That's the reality we seem to live in. But how do we know? It all comes down to the size of those hot and cold spots in the CMB. In a curved universe, light would bend as it travels, making those spots appear larger or smaller than they actually are. Imagine trying to project a movie onto a crumpled sheet. The image would distort. But the CMB's spots match predictions for a flat universe almost perfectly, like a pristine projection on a smooth screen. The kicker: a flat universe has mind-bending implications. It means the cosmos is balanced on a knife's edge, with just the right amount of matter and energy to keep spacetime from curving. Too much and it would collapse inward like a sphere, too little and it would flare outward like a saddle. This delicate balance hints at something even wilder: the universe might be infinite. No edges, no boundaries, just an endless expanse of galaxies stretching forever. Of course, probably is the key word here. The CMB's data overwhelmingly supports flatness, but cosmology loves a good mystery. Some theorists toy with the idea of a universe so vast its curvature is undetectable, like an ant on a basketball thinking it's on a flat plane. Others wonder if exotic physics, like higher dimensions, could hide tiny bends in spacetime. But for now, the flat universe is the simplest explanation that fits the evidence. Why does this matter? Because a flat cosmos reshapes our understanding of everything from the Big Bang to the universe's ultimate fate. It's a cornerstone of modern cosmology, and we owe it all to those faint microwaves whispering across the sky. So next time you stare at a horizon, remember, the universe might just go on forever, and the CMB is our roadmap to infinity. Now, let's pivot to one of the most baffling quirks hidden in the cosmic microwave background, the so-called axis of evil. This isn't some sci-fi plot twist. It's a real cosmic head-scratcher that has physicists debating whether we're missing a piece of the puzzle or if the universe is playing tricks on us. Here's the mystery. When scientists mapped the CMB's temperature fluctuations, they expected randomness, tiny hot and cold spots scattered like confetti. But instead, they noticed something eerie. Some of these fluctuations appear to align along a specific axis, almost as if the universe has a preferred direction. This defies a core principle of cosmology, the idea that the universe should look the same in all directions, no matter where you're observing from. It's like spinning a globe and realizing all the continents oddly line up along one invisible line. Why call it the axis of evil? The name, coined half-jokingly, reflects how unsettling this anomaly is for standard models. If the universe is truly isotropic uniform in all directions, these aligned fluctuations shouldn't exist. One possibility is that it's just a statistical fluke, a cosmic coincidence in the data. But the odds of that are slim, like flipping a coin 100 times and getting heads every single time. Some theorists have proposed wilder explanations. Could it be evidence of a pre-Big Bang structure imprinting itself on the cosmos? Or perhaps a sign that our universe is shaped like a torus, a giant cosmic donut, with hidden geometry warping the CMB's light? Others wonder if it's a hint of something beyond our current physics, like undiscovered forces or even traces of a neighboring universe brushing against ours in a multiverse scenario. The stakes are high because if the axis of evil is real and not just noise, it could upend our understanding of cosmic inflation, the rapid expansion thought to have smoothed the early universe. Inflation predicts randomness, not alignment. So, is the anomaly a clue that inflation needs tweaking, or is it pointing to something even more profound? For now, the debate rages on. New telescopes and deeper CMB analysis might one day solve the riddle, but until then, the axis of evil remains one of cosmology's most tantalizing loose threads. It's a humbling reminder that even our best models might be missing a piece of the puzzle, and that the universe still has surprises up its sleeve. Now, let's shift our gaze to something even more mind-bending: how the tiny ripples in the cosmic microwave background might actually be echoes of quantum jitters from the very birth of the universe. That's right, those faint hot and cold spots we see in the CMB could be the magnified fingerprints of subatomic chaos that unfolded in the first fractions of a second after the Big Bang. Here's how it works. In the earliest moments of the cosmos, everything was a seething, ultra-dense soup of particles and energy, governed by the bizarre rules of quantum mechanics. At that scale, even empty space isn't truly empty. It's a frothing sea of virtual particles popping in and out of existence, creating tiny, random fluctuations in energy. These quantum jitters, as physicists call them, were happening everywhere all at once. Then came cosmic inflation, the universe's explosive growth spurt. In less than a blink of an eye, the universe expanded faster than the speed of light, stretching those minuscule quantum fluctuations along with it. Imagine blowing up a balloon with microscopic wrinkles on its surface. By the time it's fully inflated, those tiny imperfections have grown into large, uneven patches. That's essentially what happened to those quantum ripples. They got stretched across the cosmos, becoming the seeds for the temperature variations we now see in the CMB. This idea isn't just theoretical, it's one of the strongest links between quantum mechanics and cosmology. The math checks out. The patterns in the CMB's fluctuations match what you'd expect if they originated from quantum noise. It's like finding a fossil that perfectly fits the skeleton of a long-extinct creature. These ripples didn't just stay frozen in the CMB either, they became the scaffolding for everything we see today. The slightly denser regions pulled in more matter through gravity, eventually growing into galaxies, galaxy clusters, and the vast cosmic web we observe now. But here's where it gets even wilder. If this quantum origin story is correct, then the universe we inhabit, with its stars, planets, and even us, is essentially the result of magnified subatomic randomness. It's as if the universe rolled a quantum dice in its first moments, and the outcome shaped everything that followed. Some scientists are probing even deeper, asking whether the CMB's ripples could reveal more about quantum gravity, the still elusive theory that would unite quantum mechanics with Einstein's general relativity. Others wonder if there are even subtler patterns hidden in the CMB that could point to new physics beyond our current understanding. For now, though, the connection between quantum jitters and the CMB stands as one of the most elegant explanations for how the universe went from a chaotic beginning to the structured cosmos we know today. It's a reminder that the largest structures in existence might owe their existence to the tiniest of phenomena, and that the universe's grandest mysteries often start at the smallest scales. Here's something that might make you rethink time itself. The cosmic microwave background isn't just a relic of the past. It's actively changing, cooling down as the universe expands. Picture it like a campfire slowly burning out. 13.8 billion years ago, that afterglow of the Big Bang was scorching hot, around 3,000 Kelvin hotter than the surface of some stars. Today, it's a frosty 2.7 Kelvin, barely above absolute zero, and it won't stop there. This cooling happens because space itself is stretching. Imagine drawing waves on a rubber band, then pulling it taut. The peaks get farther apart and the energy spreads out. That's what's happening to the CMB's photons. As the universe expands, their wavelengths stretch, shifting them from higher energy microwaves to lower energy radio waves. Over time, they'll become so faint and stretched that future civilizations might miss them entirely. In a trillion years, the CMB could redshift into oblivion, leaving no trace of the universe's fiery birth. But this cooling isn't just a curiosity, it's a cosmic clock. By measuring the CMB's temperature over time, scientists confirmed the universe's expansion is accelerating, driven by dark energy. Every billion years, the CMB cools by a tiny fraction, like a thermometer ticking down. And here's the eerie part. If we could see the CMB as it'll appear in the distant future, its patches would look smoother. Those fluctuations that seeded galaxies. They'd be diluted by expansion, like ink dissolving in an ever-growing ocean. The implications are profound. The CMB is our only direct window into the early universe, and it's slowly closing. Future astronomers might never know the cosmos had a beginning because all evidence of it will have faded away. It's a reminder that we're living in a golden age of cosmology, a brief moment when the universe's history is still legible. Yet even as it cools, the CMB still has secrets to reveal. Some theorists wonder if its temperature variations could hide clues about the universe's ultimate fate. Others study how cooling affects the balance between dark energy and matter, shaping the cosmos on the largest scales. One thing's certain, while the CMB is fading, its story is far from over. For now, it remains our best time capsule, a whisper from the dawn of everything, growing quieter with every passing second. Now, let's tune into something truly extraordinary, the symphony of the early universe. Those faint patterns in the cosmic microwave background aren't just random noise. They're cosmic sound waves frozen in time, echoes from an era when the universe was a seething ocean of hot, dense plasma. Picture this, in those first moments after the Big Bang, the cosmos wasn't silent. It was a roaring cauldron of pressure waves pulsing through space like the beats of a massive drum. These waves, called Baryon acoustic oscillations, started when gravity tried to pull matter together while the intense heat and radiation of the young universe pushed back. This tug-of-war created ripples, regions of slightly higher and lower density, that traveled outward at nearly half the speed of light. Over hundreds of thousands of years, these ripples left their mark on the primordial plasma, like fingerprints pressed into wet clay. When the universe finally cooled enough for atoms to form, releasing the CMB we see today, those ripples were frozen in place, etched into the microwave sky like grooves on a record. Here's where it gets mind-bending. Scientists can actually hear these ancient sound waves by analyzing the CMB's temperature variations, the most common wavelength. About 500,000 light-years across a cosmic bass note that set the rhythm for how galaxies would later cluster together. Imagine throwing a handful of pebbles into a pond. The ripples spread out in rings, and where they overlap, you get peaks and troughs. The CMB shows us those same peaks and troughs, but on a scale so vast it shaped the entire cosmic web. What's even wilder is that these sound waves didn't just vanish after the CMB was released. They kept influencing the universe. Today, galaxies are more likely to be found at specific distances from each other, roughly 500 million light-years apart, because that's where those ancient pressure waves piled up matter. It's as if the universe's first vibrations orchestrated where stars and galaxies would eventually bloom. And here's the kicker: this cosmic symphony isn't just a relic. It's a tool. By studying these oscillations, astronomers can measure the universe's expansion with stunning precision, probe the nature of dark energy, and even test theories about inflation, the explosive growth spurt that happened in the first fraction of a second after the Big Bang. The CMB isn't just a snapshot. It's a recording of the universe's earliest music, and we're just beginning to decode its notes. So next time you hear static on the radio, remember, the universe once had its own soundtrack, and its echoes are still whispering to us across billions of years. Now, let's shift our focus to one of the most puzzling cosmic riddles of our time, the Hubble tension. The cosmic microwave background isn't just a relic of the past. It's a powerful calculator that helps us measure how fast the universe is expanding right now. Scientists call this rate the Hubble constant, and the CMB gives us a way to predict it with incredible precision. Here's how it works. Those tiny temperature fluctuations we see in the CMB are like cosmic breadcrumbs. By studying their patterns, how much they've stretched over time, we can trace the universe's expansion history and calculate the Hubble constant. The latest CMB measurements peg this rate at around 67 kilometers per second per megaparsec. That means for every 3.26 million light-years you go out into space, galaxies are speeding away from us 67 kilometers per second faster. But here's where things get weird. When astronomers measure the Hubble constant using nearby galaxies and supernovas, so-called local methods, they get a different number, roughly 73 kilometers per second per megaparsec. That discrepancy might not sound like much, but in cosmology, it's a glaring mismatch. We're talking about two of the most trusted methods in astronomy disagreeing by about 9%. It's like having two high-precision clocks that stubbornly refuse to sync up. This clash is what scientists call the Hubble tension, and it's thrown the cosmology world into a fascinating debate. Could there be unseen errors in our measurements? Maybe, but both methods have been refined for decades, and the gap won't go away. Or perhaps it's a sign that our understanding of the universe is missing something bigger, like an unknown form of dark energy that kicked in after the CMB was released, or even new physics beyond Einstein's relativity. Some theorists speculate that the early universe might have expanded differently than we thought, or that dark matter interacts in ways we haven't accounted for. The Hubble tension isn't just a technical hiccup. It could be a cosmic clue pointing to groundbreaking discoveries. What's remarkable is how the CMB sits at the heart of this mystery. Its data doesn't just give us a number, it paints a full picture of the universe's expansion over nearly 14 billion years. The tension between its predictions and local measurements forces us to question everything, from the nature of dark energy to the very laws of physics. And that's the beauty of science. When the numbers don't add up, it often means we're on the verge of learning something extraordinary. So while the Hubble tension might seem like a problem, it's really an invitation, a cosmic challenge urging us to look deeper and rethink what we know about the universe's grand story. Now, let's venture into one of the wildest frontiers of cosmology, the idea that the cosmic microwave background might hold clues to parallel universes. It sounds like science fiction, but some scientists take it seriously. Here's why. When researchers map the CMB, they occasionally stumble upon strange anomalies, like oddly placed cold spots or unusual temperature patterns that don't quite fit our models. One particularly infamous example is the so-called cold spot, a vast, unusually chilly region in the CMB that defies easy explanation. Could this be a bruise from a collision with another universe? That's the tantalizing and controversial idea behind the multiverse theory. The thinking goes like this: if our universe is just one bubble in a vast cosmic foam of universes, each with its own physical laws, then occasionally these bubbles might bump into each other. Such a collision could leave an imprint on the CMB, like a fingerprint on glass. The cold spot, some argue, might be one such mark, a cosmic bruise where another universe nudged ours long ago. Now, before we get carried away, it's important to note this is highly speculative. Most mainstream cosmologists remain skeptical, pointing out that the cold spot could just be a statistical fluke or the result of more mundane cosmic structures like a giant supervoid. But the multiverse hypothesis isn't pure fantasy. It emerges naturally from certain interpretations of cosmic inflation, the theory that our universe expanded exponentially in its first moments. Inflation suggests that new universes could constantly be budding off from a larger meta-universe, creating an endless multiverse, the real kicker. If the CMB does contain signs of a multiverse, it would revolutionize our understanding of reality. Imagine confirming that our universe is just one page in an infinite cosmic library, each with its own version of physics, stars, and even life. It would mean the laws we take for granted, like gravity or the speed of light, might just be local bylaws, not universal constants. Of course, the challenge is proving it. The cold spot alone isn't enough, and other CMB anomalies could have simpler explanations. But that's the thrill of science. Sometimes the most outlandish ideas push us to ask better questions. Whether the multiverse is real or not, the CMB remains our best window into the deepest mysteries of existence. And who knows, the next odd flicker in that ancient light might just rewrite everything we thought we knew. Now, here's something that might make you appreciate the cosmic microwave background even more. It won't be around forever. That's right, the very afterglow of the Big Bang that we've been studying for decades is slowly but surely fading from view. Let's break down why this cosmic treasure is on borrowed time and what it means for the future of astronomy. The culprit, the expansion of the universe itself. Space isn't just getting bigger, it's accelerating thanks to dark energy. As galaxies rush apart, the CMB's light stretches even further, shifting it to longer and longer wavelengths. Right now, it's in the microwave range, but over billions of years, it'll stretch into radio waves, then eventually into undetectably low energy ripples. Think of it like a distant siren. As it moves away, the sound drops to a deeper and deeper pitch until you can't hear it at all. Here's the sobering part. In about 1 trillion years, the CMB's temperature will have dropped so much that it'll blend into the background noise of the universe. Future astronomers, if there are any, might look up and see nothing but empty, cold darkness where we now see the glow of the early cosmos. They'd have no direct evidence of the Big Bang, no cosmic microwave background to study. It's like losing the opening chapter of the universe's autobiography. This raises a mind-bending question. Are we living in a uniquely privileged era? Right now, we can observe both the nearby universe and its ancient light. But civilizations that arise in the far future might never know about the Big Bang or the CMB. they'd have to piece together cosmic history from second-hand clues, like the leftover whispers of galaxy motions or the faint echoes of dark matter. And it's not just the CMB that's vanishing. Over time, all but the closest galaxies will redshift out of sight, leaving future skies eerily empty. Some scientists even joke that in 1 trillion years, aliens might conclude the universe is static and eternal, with no clue it once exploded into being. So let's take a moment to appreciate the CMB while we can. It's not just a snapshot of the infant universe, it's a temporary gift, a cosmic secret we're lucky enough to decode. And who knows, the answers we find in its fading light might one day be the only clues left to remind the universe of its own spectacular birth. But here's something even more astonishing about the cosmic microwave background. It's not just a relic of ancient light. Hidden within its subtle patterns are whispers of ghostly particles called neutrinos, and these elusive travelers hold secrets about the universe's earliest moments. Neutrinos are among the most mysterious particles in existence. They're nearly massless, hardly interact with matter, and trillions of them pass through your body every second without you noticing. But back when the CMB was born, just 380,000 years after the Big Bang, the universe was so dense that even these ghostly particles left their mark. How, in those first fiery moments, neutrinos flooded the cosmos, moving at nearly the speed of light. Their sheer energy and speed warped the distribution of matter in the primordial plasma like ripples in a pond. When the CMB finally broke free from that plasma, it carried tiny imprints of those distortions, faint fingerprints of neutrino activity. Scientists call this the neutrino damping tail, and it's one of the clearest pieces of evidence we have for how these particles shaped the universe's large-scale structure. Here's why that's mind-blowing. Neutrinos are so hard to detect directly that most of what we know about them comes from labs buried deep underground. But the CMB gives us a backdoor, a way to study their influence on cosmic history without catching a single one. By analyzing the CMB's temperature fluctuations, researchers can estimate how many neutrinos existed in the early universe and even infer their combined mass. And that's crucial because neutrinos might hold answers to some of physics' biggest puzzles, like why the universe has more matter than antimatter. Even more intriguing, the CMB suggests there might be additional types of neutrinos beyond the three we already know: sterile neutrinos, which could be linked to dark matter. While this is still speculative, it shows how the CMB isn't just a snapshot of the past. It's a treasure map pointing to discoveries we haven't even made yet. So the next time you hear about the cosmic microwave background, remember, it's not just light. It's a time capsule preserving the faint echoes of particles that barely interact with anything. And in those echoes, we might just find the next revolution in physics. Now, let's shift our gaze to another fascinating way the cosmic microwave background reveals hidden secrets, this time through its shadows. You might think of the CMB as a uniform glow, but massive structures like galaxy clusters actually leave their mark on it, like fingerprints on a window. This phenomenon is called the Sunyaev-Zeldovich effect, and it's one of the most powerful tools astronomers have for mapping the invisible scaffolding of the universe, dark matter. Here's how it works. Galaxy clusters are the universe's largest gravitationally bound structures, containing thousands of galaxies, hot gas, and critically vast amounts of dark matter. As the CMB radiation travels across the cosmos, some of its photons pass through these clusters. The hot gas within them is packed with high-energy electrons, and when CMB photons collide with these electrons, they get a tiny energy boost. This interaction leaves a faint shadow in the CMB, a slight dip in its temperature at the cluster's location. It's as if the cluster took a bite out of the microwave background. But why does this matter? Because these shadows aren't just about the clusters themselves. The Sunyaev-Zeldovich effect lets scientists trace the distribution of dark matter, which doesn't emit light but exerts gravitational pull. By studying where these shadows appear and how they distort the CMB, researchers can create 3D maps of dark matter across the universe, revealing where it clumps and how it shapes cosmic evolution. It's like using the CMB as an X-ray to see the skeleton of the cosmos. What's even more remarkable is that this effect works regardless of how far away the cluster is. Unlike traditional methods that rely on visible light which gets fainter with distance, the Sunyaev-Zeldovich signal stays consistent, making it ideal for spotting clusters in the distant early universe. Some of the most massive clusters ever discovered were found this way, hiding in plain sight as subtle dimples in the CMB. And here's the kicker: this technique isn't just about mapping what's out there. It helps test fundamental physics like the nature of dark energy and the growth of cosmic structures over billions of years. In a way, the CMB's shadows are like cosmic breadcrumbs, leading us deeper into the mysteries of the universe's invisible architecture. So next time you hear about the cosmic microwave background, remember it's not just light. It's also a canvas, and its shadows paint a picture of everything we can't see. Now, let's venture into one of the most mind-bending possibilities hidden within the cosmic microwave background: cosmic strings. Imagine the universe as a vast frozen lake. When water turns to ice, tiny cracks sometimes form. Cosmic strings could be like those cracks, but in the fabric of spacetime itself. These hypothetical threads, thinner than an atom yet unimaginably dense, might have been forged in the fiery chaos of the early universe, and their ghostly fingerprints could be etched into the CMB. So, what exactly are cosmic strings? Think of them as cosmic scars, one-dimensional defects left over from a phase transition in the universe's infancy, like cracks forming as a superheated material cools unevenly. According to some theories, these strings would carry immense mass, packing more than a mountain's worth into a single inch. Yet, they'd be so thin that if one passed through you right now, you might not even notice. But here's where the CMB comes in. If cosmic strings exist, their gravitational pull would warp spacetime around them, subtly distorting the light of the cosmic microwave background. These distortions could create strange, linear patterns in the CMB's temperature map, like faint brushstrokes on an otherwise smooth canvas. Scientists have been hunting for these elusive clues for decades. Some of the CMB's oddest anomalies, like unexplained cold spots or unusual alignments of fluctuations, have sparked speculation that cosmic strings might be the culprit. For instance, certain jagged edges or sharp temperature drops in the CMB data don't quite fit our standard models. Could these be the cosmic equivalent of a scratch left behind by a string slicing through spacetime? It's a tantalizing idea, but here's the catch: no one's found definitive proof yet. Cosmic strings remain in the realm of what if, a thrilling possibility that keeps theorists on their toes. Why does this matter? Because cosmic strings aren't just cosmic curiosities, they'd be a direct window into the universe's first moments. If we could confirm their existence, it would revolutionize our understanding of fundamental physics, from quantum fields to the nature of spacetime itself. Some theories even suggest these strings could behave like cosmic time capsules, vibrating with echoes of the Big Bang. And while we haven't spotted one yet, future CMB experiments like next-generation space telescopes or ultra-sensitive ground-based detectors might finally catch these ghostly threads in the act. So the next time you look at a map of the cosmic microwave background, remember, those tiny fluctuations might be hiding more than just ancient light. They could be scars from the universe's birth, whispers of cosmic strings that shaped everything we see. And if we're lucky, one day we'll unravel their secrets, pulling on the threads of spacetime itself. Now, let's tackle one of the most puzzling gaps in our cosmic detective work: the missing large-scale features in the cosmic microwave background. Picture this: if the CMB were a symphony, we'd expect it to have deep, resonant bass notes alongside its higher-pitched tones. But when scientists mapped it, they found something odd. Those low-frequency notes were barely there, almost as if the universe had hit mute on its largest scales. Here's why this is so baffling. According to the leading theory of cosmic inflation, the early universe expanded faster than light in a fraction of a second. This process should have left behind fluctuations of all sizes, from tiny ripples to colossal waves. But when we study the CMB, the largest patterns, the ones spanning billions of light years, are suspiciously faint. It's like looking at a fingerprint and realizing the biggest walls are missing. Scientists call this the lack of large-scale correlation, and it's been a thorn in cosmology's side for decades. What could explain this? One possibility is that our models of inflation need a tweak. Maybe the universe didn't stretch uniformly, leaving some scales underdeveloped. Another wild idea: the cosmos might be far larger than we can observe, making these giant fluctuations appear diluted, like trying to spot ocean waves from a single drop of water. There's even a fringe theory suggesting gravitational waves from other universes. Yes, other universes could have interfered, effectively erasing these signals. The stakes are high because these missing features aren't just academic quirks, they're clues to how space, time, and matter itself came to be. If inflation didn't happen the way we think, it could upend everything from dark energy to quantum gravity. Future missions, like the proposed LightBird satellite or ground-based observatories with ultra-precise polarization measurements, might finally crack this case. Until then, the CMB's silence on the largest scales remains one of its most tantalizing mysteries, a cosmic whisper we're still straining to hear. So, while the cosmic microwave background has given us a treasure trove of insights, its gaps might be just as revealing. After all, sometimes what's missing tells the most compelling story of all. Now, let's turn our gaze to the future, because the cosmic microwave background isn't done revealing its secrets. The next generation of telescopes and experiments is gearing up to probe the CMB with precision so sharp it could rewrite entire chapters of cosmology. At the forefront is CMB S4, a groundbreaking project set to launch in the next decade. Imagine upgrading from a grainy black and white TV to a razor-sharp 8K display. That's the leap this mission promises. With over 20 times the sensitivity of current observatories, CMB S4 will map the CMB's temperature and polarization in exquisite detail, hunting for faint echoes of cosmic inflation and the elusive fingerprints of primordial gravitational waves. These ripples in spacetime, predicted by Einstein, could confirm whether inflation truly happened, and if so, how. But CMB S4 isn't flying solo. The Simons Observatory in Chile, already under construction, will act as a cosmic magnifying glass, scanning the sky with 500,000 detectors. Its goal: to measure the CMB's polarization patterns with such accuracy that even the faintest whispers from the universe's first trillionth of a second become audible. Then there's LightBird, a Japanese-led satellite mission designed to orbit 1,000,000 miles from Earth, far from our planet's interference. LightBird's specialty: peering into the CMB's oldest light to test whether inflation left behind a unique swirl in the polarization, a smoking gun for the theory. Why does this all matter? Because these missions could settle debates that have simmered for decades. For instance, if they detect primordial gravitational waves, it would confirm that inflation wasn't just a rapid expansion. It was a quantum-driven explosion, tying Einstein's gravity directly to the subatomic world. On the flip side, if they find nothing, it might mean inflation wasn't as violent as we thought, or that an entirely new framework like string theory or loop quantum gravity holds the key. And the surprises don't stop there. Future experiments might also spot anomalies like those mysterious cold spots or odd alignments that hint at phenomena beyond our current physics. Could they be evidence of parallel universes brushing against ours, or cracks in space-time left by cosmic strings? Upcoming data could turn these wild speculations into testable science. The takeaway: we're on the cusp of a golden age in CMB research. With each new mission, we're not just tweaking our cosmic map, we're redrawing it, and who knows? The next big discovery might be hiding in those ancient microwaves, waiting for the right telescope to uncover it. So, while the cosmic microwave background has already transformed our understanding of the universe, its deepest secrets are still locked away, and the keys are coming soon. Here's your seamless continuation, blending warmth with cosmic awe while keeping it accessible yet profound. Now, here's the ultimate cosmic twist, something that connects you directly to the Big Bang's afterglow. Those atoms dancing in your body right now, they're not just stardust, they're CMB leftovers. Let's unpack that. When the universe was a seething plasma soup, hotter than the core of the sun, it was too dense for atoms to form. Light couldn't travel freely, it just bounced around like a pinball. But 380,000 years after the Big Bang, things cooled just enough for protons and electrons to finally link up, creating the first hydrogen and helium atoms. That moment when light broke free is exactly when the CMB was born. Now fast forward billions of years, those primordial atoms got recycled through generations of stars, fused into heavier elements like carbon and oxygen in stellar furnaces, then scattered across the cosmos by supernova. Eventually, they ended up in the gas clouds that formed our solar system, and eventually you. So the iron in your blood, the calcium in your bones, they trace back to that same scorching plasma that glowed as the CMB. Think of it like a cosmic family tree. The CMB is the universe's baby photo, and we're the grown-up version of that baby, literally made from its leftover ingredients. Even the oxygen you're breathing right now was once part of that primal fireball. But here's the kicker: every time you microwave leftovers, you're bathing your food in the same type of radiation that fills the cosmos. The universe is, in a way, one giant microwave oven, and we're the reheated cosmic pizza. So next time you gaze at the night sky, remember, you're not just looking at the universe's history. You're carrying a piece of it inside you. The CMB isn't just light on a telescope screen, it's the echo of your atomic ancestry. Talk about a mind-bending family reunion. And with that, we've reached the end of our cosmic journey through the echoes of the Big Bang. From the CMB's accidental discovery by Penzias and Wilson to its role as a time capsule for the universe's first atoms, we've uncovered 25 astonishing truths about this ancient light. It's not just a relic of the past, it's a living clue helping us decode the universe's deepest secrets, from dark matter's invisible grip to the mysterious push of dark energy. Think about it, this faint microwave glow is the ultimate cosmic detective. It's mapped the geometry of the universe, revealed quantum jitters frozen in time, and even hinted at mind-bending possibilities like parallel universes. And as we've seen, its story is your story too. Every atom in your body carries a whisper of that primordial fireball, linking you directly to the universe's fiery birth. So here's my challenge to you. Which fact blew your mind the most? Was it the pigeon droppings that led to a Nobel Prize, the eerie axis of evil anomaly? Or the humbling idea that future civilizations might never detect the CMB at all? Drop your favorite in the comments. I'd love to hear what cosmic nugget stuck with you. If this deep dive into the universe's oldest light left you hungry for more, don't forget to hit like, subscribe, and ring that notification bell. There's always another cosmic mystery waiting just around the corner, and I'll be here to unpack it with you. Until next time, keep looking up and remember, you're not just observing the cosmos, you're made of it.